In the previous lecture, we talked about magnetic fields in general. Now I want to talk about how currents can create magnetic fields. In fact, any moving charge will create a magnetic field. And what is a current? Well, it's just charges flowing somewhere. So current is the flow of charge, and moving charges create magnetic fields. Therefore, currents create magnetic fields. The simplest current I can think of is a current in a long, straight wire. And indeed, a current in a long, straight wire will create a magnetic field. Here we see a wire. It's carrying a very strong current, and we've sprinkled some iron filings around it, and you can see they've aligned themselves in this circular pattern. And so here's a little schematic of this exact situation. We see that the magnetic field forms these rings around the wire. And we see that the magnetic field gets weaker as I get farther from the wire, as indicated by the increasing spacing of these magnetic field lines. Okay, so a wire creates a magnetic field. Okay. That magnetic field forms rings around the wire. There's kind of two different ways that could face. Notice if I've got a current up, then I get the compasses all aligned in this sense right here. And if I have a current down, then I get the compasses aligned in a different sense. When viewed from the top, we see that the north pole here is kind of pointing around in a counterclockwise sense, and here we see that the north poles are pointing in sort of a clockwise sense. So, how do we know which is which? Well, we have a mnemonic for that. It is a physical mnemonic. It is called the right-hand rule, and you're going to have to practice this one on your own. You're going to have to practice it with your right hand. It's going to take a little doing to get it right. Okay, so let's see how that works. You've got a wire. Here is a long, straight wire. And in order to figure out whether our magnetic field wraps around like this or like this, we need to use the right-hand rule. How does that work? Well, take your right hand. That's a hint in the name of it. You take your right hand and you put your thumb in the direction of the current. So in this case, if my wire was carrying a current upwards, I would put my thumb in this direction, in the direction that the current is going. Now my fingers will wrap in the sense of the field, which means that the field points like this. Right hand, thumb in the direction of the current, the field points like this. If I was to view this from the top, I would say, oh, that is a counterclockwise field. Okay, sounds easy. Takes a little bit of practice. It's not too bad once you get your brain around it. Now, magnetism is fundamentally a three-dimensional phenomenon. It just is. Which is surprising. It's actually the first thing since rotation, way back in like chapter, 6 or 7 or something, that we've encountered something that is fundamentally a three-dimensional phenomenon. I can ask you I can ask you electric field questions that are 1 or 2 dimensions without losing any of the actual real physics. It makes it a little bit easier to ask you a 1 or 2 dimensional electric problem instead of a 3-dimensional one. But it doesn't lose any of the fundamental physics. With magnetism, you just can't do that. It's a 3-dimensional topic. It just is, as we'll see going through this. That means that we need to learn a new way to draw vectors that are not just side to side. You know, if I've got a little Timmy pushing in that direction, well, then I just go like this, right? There you go. There's the force of little Timmy pushing in that direction. But what if Timmy is pushing out of the board? How would I draw that on my board? I could do some kind of perspective or something, but if I'm trying to do a perspective, that doesn't work. Right? We need something that's just very schematic and analytical. So instead of trying to draw some perspective view, it's always just flat on, and if something's coming out of the board, we use dots. A vector out of the board looks like this. And a vector into the board looks like this. So this would be out. This is in. That is to the right. You probably didn't need physics class to know that. I remember this by thinking about a bow, like an arrow from a bow and arrow. This is like I'm looking at the tip of that bow and arrow, and this is like I'm looking at the feathers of that bow and arrow, of that arrow. So that here's the feathers of the arrow, it's pointing in. here's the tip of the arrow. It is pointing out. Now, this is super standard. Our book likes to label currents with a circle around them. That is less standard, but our book is very consistent about it, and I will be as well. So that is a current into the page, and that is a current out of the page. You can see it's sort of like a schematic of a wire, with this indicating the direction of the current. Okay, again, we just need a way to draw those vectors when they aren't existing in a two-dimensional world. Okay, so if a long straight wire creates a magnetic field, well, what happens if I take that wire and I bend it into a loop? Guess what? That creates a magnetic field too. It just has a little bit of a different shape. And here we see a quick schematic of it. You can see that, if you just focus on one side or the other, it's not that dissimilar from a wire. It still wraps around it, either in a counterclockwise sense or a clockwise sense, depending on whether the current is going in or out. And we can see here, on the top of this loop shown down there, we see that the current is rotating in a counterclockwise sense. And so, we could rotate our fingers in a counterclockwise sense using the right-hand rule that we learned, which I'm going to call right-hand rule number 1 because we're going to learn another one. For a field rotating in a counterclockwise sense, that means that the current is coming out of the board, out of the page. On the bottom there, we see a field rotating in a clockwise sense, and that indicates a current going into the board by right-hand rule number 1. We can have a little bit different visualization of that by looking at, here's a side view of that loop. Here is a sort of perspective view of that loop. And then here we see the view that we were initially confronted with here. And indeed, here we see that on top, the current is coming out of the board. And on the bottom, it is going into the board. So we can use right-hand rule number 1 to determine the direction of the field in our current loop. So here we see our current loop, and if the current is going like this, then we see that the field is coming towards me on the inside and towards you on the outside. Again, we're using that right-hand rule number 1, as indicated here. Near the wire, the lines are almost circular, as we would expect from a current-carrying wire, but in the middle here, they're pretty much just straight. Notice we get all one direction on the inside of the loop, all one direction on the outside of the loop. Okay, let's practice this a little bit. Really and truly, getting this right-hand rule right, it requires a fair amount of practice. It's not hard, but it takes a bit of practice to where you can just confidently do it every time in all different situations. So I have a series of clicker questions. They're really intended to be practice, and I encourage you not to just roll through them and watch me do it. I really, really encourage you to stop the video, get out your right hand, if you can find it, and do it yourself. And reach a positive conclusion. Write it on your paper. Commit to an answer, and then see if you were correct or not. That's how you really tell if you're right or wrong. It's easy to say, oh, I think maybe it's B, and then I show C, and you're like, oh yeah, I guess that makes sense. But you never really did it on your own, right? So I really, really want you to commit to an answer, write it down on the paper, and then continue the video and see whether you were right or not. If you were wrong, don't just let me tell you that. Figure it out, go back, do it again, see that you're wrong. See that yours has a logical flaw in it. Okay, here we go, going through it. Here we see a slice of a current loop, and I am wondering, what is the direction of the magnetic field at this point? We see that the current is coming out of the board on top and into the board on the bottom. So, is the field at this point to the left, up, to the right, or down? Why don't you pause the video, and I will see you on the other side. All right, so here's my loop. I've got my current coming out of the board on top and into the board on the bottom. Out of the board on top looks like this, right? And so out of the board on top means that the field is going towards me outside the loop, but inside the loop, it's going in that direction. Okay, so again, going towards me on the top of the loop, and I guess I'll go over here in the other direction on the bottom of the loop. Save me some wrist strain. Okay, so again, what did we just observe? We just observed a field that is wrapping around like this. Okay, how about on the bottom? On the bottom, we have a field, or a current that is going into the board. That means that it is to the right, inside the loop, and to the left, outside the loop. To the right, inside the loop, to the left, outside the loop. Aha! Okay, so now we've got a sense of the direction. Notice inside the loop, the field is going in that direction. Outside the loop, it is going in the opposite direction. I'm going to call that to the right in PowerPoint degrees. Now, I do want to point something out here. You saw me kind of struggling here, right? I wasn't just trying to show off my guns. I was struggling there, right? Why? Sometimes it's just a little bit tricky to get your hand in the right place. There's a little bit of a shortcut when we're dealing with loops and something called solenoids that we'll get to in a minute. It is still right-hand rule number 1. However, we can simplify it a little bit, and we switch our fingers and our thumb. We're going to call this the alternative version of right-hand rule number 1, because we haven't even gotten to right-hand rule number 2. This is the alternative version of right-hand rule number 1. It is effective for loops and something we haven't talked about yet, solenoids. You curl your fingers in the direction of the current in the loop, which would be like this, out of the board on top, into the board on the bottom. Your thumb points in the direction of the magnetic field on the inside of the loop. Alternative, right-hand rule number 1, I will state it again. You curl your fingers in the direction of the current. Your thumb curls in the direction of the field on the inside of the loop. Your thumb points in the direction of the field on the inside of the loop. That is the alternative version of right-hand rule number 1, and it can avoid some wrist strain when you're dealing with loops. Notice that on the inside of the loop, the field is all in the same direction. Right? So once I've figured it out on top or on bottom, that it's going that direction, it is the same everywhere in the loop. The magnitude is not necessarily the same, but the direction is the same everywhere on the inside, and the direction is the same and opposite everywhere on the outside. Okay. Here's another one. Where is the north magnetic pole of this current loop? That's a tricky one. Why don't you give it a shot? I'll see you on the other side. Okay, in order to answer this question, we really need to know what the shape of the magnetic field is like. Here's my loop. Right-hand rule number 1 will help us tell us the direction of the field on the inside of this loop. So let's look at that. Let's see. So here we've got a current that is going into the board. Right-hand rule number 1 tells us that the magnetic field on the inside is going down. On the outside, it's coming up. So that means that the field is wrapping around like this. And how about over here? How about on this side? On this side, we have a current coming out of the board. That tells us that the field is going up on the outside and down on the inside. Again, the direction is the same everywhere on the inside of the loop. Now, those are two magnetic field lines, but we know the basic shape from the field of a loop. We saw that in a slide a couple of seconds ago. And so we could add a couple more here. Again, right-hand rule number 1 told us that the field on the inside of the loop was going down. Let's confirm that the alternative version of right-hand rule number 1 gives us the exact same answer. In that one, used only for loops and solenoids, we curl our fingers in the direction of the current and our thumb points in the direction of the field on the inside of the loop. We get the same exact answer with less strain on our wrists and elbows. Now, what's our rule for north and south poles? We know that that magnetic field lines always go alphabetically. On the outside of a magnet, they go from north to south. Here I see a field line exiting here, entering here. We know they go from north to south. Therefore, the bottom of my magnet is the north pole. Okay. And indeed, PowerPoint agrees. Ooh. So here's a quick sketch that's much tidier than mine is. Notice it still has all of the features, however. Down in the middle of the loop, up on the outside of the loop, everywhere on the inside of the loop has a field in the same direction. Notice that this does look just like a bar magnet. And so it really does have a well-defined south pole on the top and a well-defined north pole on the bottom. One other thing to maybe point out here is that magnetic field lines always form loops. So we see that they clearly form loops here for our current loop, but it turns out that those magnetic field lines connect back on the inside of the magnet, which means that this rule we have, that magnetic field lines go north to south, that only applies outside of a magnet. Because inside of a magnet, they have to reconnect, which means they go south to north inside of a magnet. I prefer to just remember what it does on the outside, and then the inside just makes sense if they're going to connect in a loop. Okay, another shape that we are concerned about is a solenoid. A solenoid is a series of current loops placed along a common axis. Okay, so what's the difference between a loop and a solenoid? This is something that trips up students quite a bit. Well, a solenoid turns out to be a very useful device. They're found in cars, sprinkler valves have solenoids in them. They're all over the place, and they are a very useful tool. So the difference between a loop and a solenoid in physics-ese, which is the language we speak around here, is that a loop is all coiled up upon itself. So a loop would look like this. A loop has no length, right? These coils are all on top of each other. I would call this a loop, but now I have turned it into a solenoid, okay? So a solenoid has some length in this direction, whereas a loop is all squished together. So that is a little bit of physics-ese that can be a little bit tricky to remember. But a solenoid turns out to be a very useful thing for a number of reasons, one of which is because it can create a very strong magnetic field. It's essentially a whole bunch of loops, which on their own create a magnetic field. And if they get the current going in the same direction, then the magnetic field from all those loops adds. And if we stretch it out, we get some spatial extent. We can get a very strong, very uniform magnetic field on the inside of this solenoid. That's why they're so useful. And so here we see sort of a schematic. We see current coming in one side, it wraps around, and then it comes out the other side, giving us a magnetic field as shown here. And here is the same sort of image. Here we see some iron filings thrown down to show us the shape of the magnetic field. And notice we get this really nice uniform magnetic field on the inside. Parallel, evenly spaced lines indicate a uniform magnetic field. And that's the point of the solenoid. So inside, the field is reasonably uniform and much, much stronger than it is on the outside. We're going to talk about some equations in the next lecture, but when we're talking about solenoids, we assume that the inside is uniform and that the field outside of the solenoid is actually zero. It's not literally zero, but it is much, much, much weaker than it is on the inside, which is part of why solenoids are so useful. Let's practice using the right-hand rule. We can still use right-hand rule number 1 to answer this question. What is the direction of the current as viewed from the top? And in this case, these black arrows indicate the magnetic field. Why don't you give it a shot, and I'll see you on the other side. Okay, so here I've drawn my solenoid there, and here I have constructed a model. And so this is what our solenoid looks like, and it tells us that the magnetic field is coming up on the inside. And so I would suggest that this is a great chance to use right-hand rule number 1, the alternative version, because we know that the field on the inside is going up, and so we simply curl the fingers of our right hand in the direction that the current is going around the loop. And so we can see that it's going in this direction right here, and so therefore it is coming in this side and out this side. To my drawing, in this side and out this side. Right-hand rule number 1, alternative version. Thumb in the direction of the field on the inside, fingers curl in the direction of the current. So it's rotating like this. Now let's answer the question. I'm looking down upon it from the top. As I look down upon it, I see that that is counterclockwise. Now notice that right-hand rule number 1, the original version, would work just as well, right? We've got a field going up on the inside, therefore, up on the inside, the current is coming out on my right side and in on my left side. So it's coming in over here, out over here, in over here, out, in, out, in, out. My current must be going like this. When viewed from atop, I still get counterclockwise. All right, a little bit tricky, but we're starting to see why magnetic phenomena is fundamentally a three-dimensional phenomenon.